In the digital world, is artificial intelligence poised to be our greatest protector, or maybe our most dangerous adversary? Today, we're taking a deep dive into a really interesting new framework, one that actually puts a real dollar value on AI's role in cybersecurity.
Yeah, it's a critical question, isn't it?
Yeah.
And that's exactly why researchers at Stanford and UC Berkeley developed something quite groundbreaking called BountyBench. It's really designed to finally give us an empirical, a real-world way to measure what AI can actually do out there.
Okay, so our mission today then is to unpack what Bounty Bench is, how it manages to quantify what these AI agents can do, finding, exploiting, even patching cybersecurity vulnerabilities. We'll reveal some pretty surprising facts about their performance and, crucially, their economic impact. So if you're looking for a shortcut to getting up to speed on this absolutely critical topic, well, you're in the right place. So maybe let's start with the current state of play. We all know cybersecurity is just this constantly evolving landscape, right? For a long time, traditional methods for evaluating cyber capabilities have been, well, our go-to. Things like Q&A benchmarks, where models answer security questions or analyzing isolated bits of code. Even capture the flag exercises, CTFs, have been useful. But I guess the question is, if these older benchmarks were so limited, what's the biggest blind spot they left us with? Especially when trying to understand AI's real security chops.
That's a great question. And it really gets right to the heart of why Bounty Bench was needed. Because while those existing benchmarks, they've played a role, they definitely fall short in a few key areas. First, they often aren't really comprehensive or real world enough. It's like,
Yeah.
imagine trying to test a self-driving car on a perfectly flat, empty road versus, navigating a busy city street. Real systems are incredibly complex, and actually setting them up for testing is difficult. It's tricky. And this can sometimes lead to tasks that are, well, broken, or maybe they even introduce new vulnerabilities just in the test setup itself, which obviously makes the results less meaningful.
Right. So not really reflecting the true chaos and the messiness of the real digital world.
Precisely. And second, these benchmarks, they very rarely cover both offensive and defensive capabilities within the same system. So you might see how an AI can attack, but you don't get the corresponding insight into how it defends, or, vice versa. It makes it hard to get that full picture, that balance. Third, they often just show what happened, like, okay, an exploit worked, but not why. Why did the vulnerability exist? How did it actually work under the hood? We need to understand the root cause, right? Not just the symptom. And finally, cybersecurity systems evolve so fast. Things change constantly. But most benchmarks are static snapshots. They fail to capture how AI performs across different versions, different stages of a system's life. It's like trying to measure a moving target with a ruler that doesn't move.
Yeah, it sounds like we've been trying to catch a ghost with a net. A bit futile. So what kind of dynamic sort of living framework did the Stanford and Berkeley teams come up with? How does Bounty Bench actually manage to bridge these gaps?
Well, BountyBench is genuinely innovative. It's the first framework that's specifically designed to capture both offensive and defensive cyber capabilities, and critically, in evolving real-world systems. Its core innovation, the really clever part, is integrating real-world bug bounties. These aren't just theoretical problems. They have actual cash prizes attached, ranging from, maybe $10 up to a pretty substantial $30,485. And BountyBench uses these real dollar values as a direct metric. It quantifies the economic impact of how well an AI agent performs.
Using real money as a metric, that's definitely a novel approach. But I wonder, does quantifying the impact just in dollars truly capture the full scope? What about things like reputation or long-term trust after a breach?
That's a really thoughtful point. And you're right, it doesn't capture everything. No single metric probably could. But what it does do is provide a concrete, universal metric that was just missing before. It lets us directly compare the economic value of what different AI agents can achieve offensively or defensively. And the scale of this benchmark is pretty impressive too. It includes 25 diverse systems, all built from complex, actual real-world code bases. Within these systems, BountyBench features 40 distinct bug bounties. And what's particularly relevant here is that these bounties cover 9 of the OWASP top 10 risks.
Oh, wow. Right.
Yeah, for anyone listening who isn't familiar, the OWASP Top 10 is basically a globally recognized list of the most critical security risks for modern web applications. So we're talking about really significant vulnerabilities like broken access control, insecure design, software, and data integrity failures.
Well,
Serious stuff.
And the realism, you mentioned that earlier, that sounds like it was absolutely key. It sounds like they went to, well, enormous lengths to make these test environments feel authentic.
Oh, absolutely. They really did. To ensure that realism, the environments were all manually set up. which involves, installing all the necessary packages, configuring servers correctly, hydrating databases with realistic data. That alone must have been a Herculean effort, honestly. And then for the automated evaluation part, they created human-validated exploits, patches, and these crucial things called invariants.
Invariants. Okay, what are those exactly?
Think of invariants as like the system's core rules, its DNA. They're fundamental properties that must always hold true for the system to function correctly, like ensuring one user absolutely cannot access another user's private data. These are essentially built-in health checks. They guarantee that when an AI suggests a patch, it doesn't fix one problem only to break 10 other things somewhere else. So it's this comprehensive living environment designed to really mimic real-world cybersecurity challenges.
Okay, so BountyBench defines 3 core task types, mirroring that real-world vulnerability lifecycle: detect, exploit, and patch. Let's start with detect. Finding new vulnerabilities. How does that work within BountyBench?
Right, so detect is what they call a snapshot-level task. The AI agent gets access to a system's environment and its complete code base at a specific point in time. Its mission is basically to find any vulnerability associated with that system snapshot. And this is the crucial part: create an executable exploit for it. Think of it as an open-ended zero-day hunt. The AI is looking for something previously unknown, something not documented.
Okay, so an AI finds something, claims it's a 0-day. How does BountyBench rigorously check that? How do they know it's a real specific vulnerability and not just, I don't know, a fluke or the AI just crashing the system in a general way? Is there a clever mechanism for that precision?
Yes, there is, and it's actually quite neat. They've created a new detect indicator specifically for this purpose. What it means is a successful exploit has to first work on the vulnerable system, all right? But then it also has to fail when run against a patched version of that exact same system. This two-step process proves the AI truly found a specific bug and didn't just, break something randomly.
Okay, that makes
Right.
sense.
Yeah, and a great example they gave is with the Lunary AI platform. It's a real AI developer platform.
Sure.
An AI agent successfully detected what's called an IDOR vulnerability. That's insecure direct object reference. Basically, in this case, user B could delete user A's project simply because the underlying code forgot to check if user B was actually authorized to do that for user A stuff.
Ouch. Classic mistake.
Exactly. So the agent's successful detect submission involved a whole sequence. It had to authenticate as both users, retrieve user B's projects, then try to delete user B's project using user A's credentials, and finally confirm the deletion worked. That comprehensive test sequence is what validates a true zero-day detection.
Right. So next up is exploit, which is more about leveraging vulnerabilities that are already known. How does this differ from detect?
So exploit is different. It's a vulnerability level task. Here, the agent isn't hunting in the dark for a new bug. Instead, it's provided with specific details about an already known vulnerability, maybe from a bug bounty report someone filed, along with something called a verifier. Its job is then simply to output an exploit script or sequence that satisfies what that verifier is looking for.
Okay, so building on our Lunary IDOR example, for the exploit task, the agent isn't searching for a needle in a haystack anymore. It's essentially given the map coordinates to the vulnerability. Its success isn't about discovery, but about its ability to precisely execute the exploit. Like, given user A's project ID, the AI would need to log in as user B and successfully delete user A's project using B's credentials. It demonstrates a different but equally important skill: taking known information and turning it into a targeted, effective attack.
It's exactly right. It's about operationalizing known intelligence. And that leads us to the final pillar, which is patch, all about fixing things. Patch is also a vulnerability level task. The agent gets environment access, the details about a specific known vulnerability, and its objective is to actually update the code to remove that vulnerability.
Okay, so sticking with the Lunary IDOR, a successful patch you mentioned involved adding something like an orgid to a SQL query line, a small but critical change. But what happens after the AI applies that patch? How does BountyBench make absolutely sure it fixed the problem without, accidentally breaking something else in the process?
Yeah, that's the crucial part, isn't it? The evaluation for patching is extremely robust, as it should be. After the AI applies its proposed patch, 2 critical checks happen automatically. First, all those system invariants, those fundamental health tests we talked about earlier, they must still pass. This ensures the patch didn't break other essential functions or introduce sneaky new bugs.
Right. Don't fix one hole by creating 2 more.
Exactly. And second, the original exploit, the one that demonstrated the vulnerability in the first place, must now fail against the patched code. It's this dual verification invariance pass exploit fails that confirms the patch actually works and is safe. It didn't just paper over the crack, and it didn't destabilize the system.
Okay, that's a thorough process. So who are these AI agents being put through their paces? The research looked at 5 different ones: Claude Code, OpenAI, Codex CALI, and then 3 others called custom agents. These custom agents were built using different underlying large language models: GPT 4.1, Gemini 2.5 Pro Preview, and Claude 3.7 Sonnet Thinking. What's the main difference between, say, Claude Code and one of those custom agents? How do they operate?
That's a good question. The paper describes Claude Code as more of an agentic coding tool that lives in your terminal, and OpenAI Codex CLI as a lightweight coding agent. They seem more integrated, maybe with specialized tools specifically designed for code manipulation. The custom agents, on the other hand, are described as often executing raw bash commands directly within the testing environment, which was Kali Linux in this case. This gives them potentially broader capabilities, but maybe a less refined, less targeted set of actions for coding tasks specifically.
Okay, so different approaches. And what about the performance? What were the key takeaways?
The performance insights are quite telling, yeah. Overall, the big picture is that detecting those zero-day vulnerabilities in the detect task, that remains incredibly challenging for all the agents tested. The top success rates were hovering around a pretty low 5%. It's just hard. However, where the agents really showed strong performance, surprisingly strong perhaps, was in exploiting known vulnerabilities and patching them.
That's a really significant distinction. So there's much better, currently at least, at reacting to known issues than proactively finding completely new ones. Was there a clear winner across the board, or did different agents excel at different things?
Oh, their strengths definitely varied, which is fascinating in itself. If we look at the top performers task by task, for patching, OpenAI Codex CLI was remarkable. It achieved a 90% success rate. Claude Code was also very strong, close behind at 87.5%. Really impressive defense. For exploiting known vulnerabilities, the leader was actually one of the custom agents, the one using Claude 3.7 Sonnet Thinking. It hit 67.5%.
Interesting.
Yeah, and what's particularly striking is this kind of offense-defense imbalance that emerged. OpenAI Codex CLI and Claude Code showed noticeably higher defensive capabilities, those high patch scores, compared to their offensive scores. Their exploit scores were only 32.5% and 57.5%, respectively. The researchers suggest this might be because of their specialized custom coding tools, which seem very effective for patching tasks.
Right, tools built for the job.
Exactly. Whereas the custom agents, executing more general commands, they were more balanced between offense and defense. Their exploit scores were in the range of 40% to 67.5%, and their patch scores were between 45% and 60%. So different profiles.
And I noticed they also tweaked the task difficulty by giving the agents different amounts of information, ranging from no info, basically, go find something, all the way up to giving them the full bug bounty report with all the details. What effect did that extra information have?
Yeah, that was a crucial part of the experimental design, testing how context helps. And it made a big difference, especially for the detect task. For detect, providing even basic information like the common weakness enumeration, the CWE identifier for the vulnerability type, significantly increased the total dollar value of the bounties the agent successfully detected. With absolutely no info, the total value found was $5,855 across all agents. But just by providing the CWE, that jumped up to $10,275.
Wow, quite a jump.
It really is. It suggests that even a small nudge, a bit of guidance, can make a big difference in AI's ability to find valuable vulnerabilities. It kind of points towards a future where maybe human security researchers collaborate effectively with AI by feeding it that crucial context, right? Humans provide the hints, AI does the heavy lifting.
This whole deep dive, it's revealing not just technical ability, but actual quantifiable economic value for these AI agents. So if I'm hearing this correctly, what we're seeing isn't just a technical step forward, it feels like a potential shift in the economics of cyber defense. What does this actually mean for things like bug bounty programs or even just the broader cybersecurity industry?
I think it means AI agents are already demonstrating a clear, measurable, positive economic impact in cybersecurity defense. Right now. They aren't just theoretical possibilities anymore, they're generating tangible value. The study put numbers on this, and they're pretty impressive. Collectively, the AI agents completed approximately $47,821 worth of patch tasks based on the associated bounty values.
$47,000 just in patching.
It's in patching. And OpenAI Codex CLI alone contributed over $14,000 of that. Even on detection, where success rates were lower, remember, the vulnerabilities detected with no info still map to a total bounty value of $5,855. And as we just said with that CWE info boost, it rose to $10,275. What's really interesting is that for many of these agents, the calculated value of the bounties they earned for detecting and patching significantly exceeded the estimated token cost of actually running the AI models.
So, potentially a positive ROI already?
Potentially, yes, in certain scenarios. Imagine how this could empower, say, smaller organizations or even individual open source developers. They could use AI to help fortify their systems in ways that might have been too expensive or time consuming before. It really puts a potential price tag on proactive security effort by AI.
What's also fascinating isn't just the quantity of fixes, but the quality. You mentioned OpenAI Codex CLI had that super high 90% patching success rate. But did those patches actually hold up? Did they fix the bug without breaking other things?
That's a huge point for practical application, you're right. And it highlights a key difference they found between the agent types. OpenAI Codex CLI specifically showed a very structured approach. Out of the 39 patches it generated that successfully stopped the exploit, an impressive 36 of them, that's 92.3%, also passed all the associated invariant checks.
Okay, so they were generally safe patches.
Exactly. It means the patches reliably fix the issue without breaking other parts of the system or introducing new bugs. That's critical for real-world deployment. The custom agents, which, remember, often lack those specialized coding tools, sometimes struggled more with this aspect. Their patches might have stopped the exploit, but failed some invariant checks, meaning they weren't always safe to apply without human review.
And what about the knowledge cutoff problem? AI models are trained on data up to a certain point. Did these agents only do well on vulnerabilities that were already known before their training ended, or could they handle newer stuff?
That's always a key question with LLM's generalization versus just memorization. The researchers looked into this. While about 85% of the bounties in their data set were publicly disclosed fairly recently, like in 2024, early 2025, the agent still managed to succeed on tasks involving vulnerabilities that were disclosed after their specific model's knowledge cutoff date.
Oh, interesting.
Yeah, it strongly suggests they possess some level of generalized understanding and reasoning ability. They're not just recalling facts they were trained on. They seem to be able to figure things out, apply patterns to new situations, which is exactly what you want.
Of course, there's always the critical ethical consideration here. Cybersecurity tools are inherently dual use. They can be used by the good guys and the bad guys. How does this research handle that ethical tightrope?
That's a very valid and important concern. The study includes an ethics statement that addresses it directly. They argue that this kind of research provides crucial empirical evidence, actual data that's needed for AI safety evaluations, and to help inform sensible regulatory decisions down the line. And by specifically focusing a large part of BountyBench on patching capabilities, they aim to deliberately accelerate research in defensive AI, hoping to kind of tilt the scales towards security and safety. The goal is explicitly to better equip the defenders.
And like any good piece of cutting-edge research, the paper acknowledges its own limitations and points towards what needs to happen next, right? What are some of those hurdles they still see?
Yeah, they're quite upfront about that. For one, adding new systems and new tasks to the BountyBench framework is still a very manual, very time-consuming process. They mentioned it can take tens of hours per task, which limits scalability. There are also ongoing evaluation challenges. The current automated evaluators, while sophisticated, aren't absolutely perfect, and the human-written invariants and exploits, while validated, could potentially be improved over time for even higher confidence in the results.
So continuous refinement needed.
Exactly. And future work they identified includes things like tracking system evolution more dynamically so, continually adding new vulnerabilities to existing systems in the benchmark as they get disclosed in the real world. Also, adding even more diverse types of vulnerabilities and exploring how allowing agents to use other tools, like maybe a web browser or custom scripts, might affect their performance. It's very much an ongoing effort to keep the benchmark realistic and comprehensive.
Well, we've taken quite a deep dive into BountyBench today. It's clearly a remarkable framework, bringing these real-world economic metrics into evaluating AI and cybersecurity. We've seen these AI agents show some really impressive capabilities, especially, it seems, in the critical areas of exploiting known issues and patching vulnerabilities. They're proving they can have tangible value in digital defense right now.
Absolutely. This is really pioneering work. It doesn't just quantify AI's current impact, but it also lays down a crucial empirical foundation, solid evidence for understanding and hopefully guiding the development of AI safety and security going forward. It really highlights AI's tremendous potential as a genuinely powerful tool, one that could significantly enhance system safety and security in our increasingly digital world.
So for you, our listener, here's maybe a final thought to chew on as we wrap up. If AI agents can already find and fix vulnerabilities that are worth thousands of dollars, how might the roles of human cybersecurity experts transform in the coming years? And what new opportunities or maybe new challenges will this ongoing evolution bring to the forefront of digital safety for all of us? Something to think about.